Okay, so let's look at skeletal system. Some of this will be a bit of a review because, we did it under tissues. The rest of it, of course, is new. Again, make sure you go through key concepts. You must know every one of those key concepts. Read all your notes really, really carefully. Every sentence and word matters. Keep your PowerPoints with your notes and kind of compare the two, okay, and see what is given. So let's begin. So let's look at the skeletal system. So it is divided into, if you look at the parts of the skeletal system, this we did actually in introduction. Remember, we had, even the whole body, we did it into an axial part, which is right in the center. So this is the axial portion, right? And then the appendicular part is in the limbs. It's called appendicular because the limbs came off as what were known as appendages. When the fetus was developing, the limbs really appeared as tiny little limb buds, which are called appendages, and that's where the appendicular word comes from. So the appendicular skeleton is the skeleton of the limbs, the upper and lower limbs. The axial skeleton is, as you can see just from this picture, you can see would be the skull, the entire vertebral column, the thoracic cage, and the pelvis together, okay? We also have cartilages in skeleton. When we talk of skeleton, we tend to kind of restrict ourselves sometimes to bones only, but we have cartilages too in various areas, like your nose, for example, your ear, the costal cartilages, then articular cartilage. So, this is giving you an example of where you would find these different types of cartilage when we do, and we did that in tissues. Remember fibrocartilage in places where you need a lot of strength, like the intervertebral discs and in the pubic symphysis. Elastic cartilage is in the ear and also in your larynx, which is your voice box. And hyaline cartilage is most areas of the body, your nose, your articular cartilage, So go back and look at your tissues notes to see where these cartilages are. And then we have another bone that I specifically wanted to mention here because it's often kind of missed when you're looking at the skeleton. This is called the hyoid bone. It's a very, very tiny bone up here just below the skull. It's the one bone in the body which does not articulate. In other words, the word articulate is used to form joints. When you say articulate, you mean it forms joints. This one doesn't form a joint with any other bone, but actually is just suspended from the skull by ligaments. There's a ligament called stylohyoid ligament. There's another ligament. You don't need to know these names, but I'm just telling you that it suspends it, okay? Now let's look at the functions of the skeletal system. Quite obviously, protection is the first one that comes to mind because, it's strong, stiff, rigid, so it protects a lot of the internal organs. Provides a framework where muscles can attach, and with the help of these muscles it causes movement and it helps you to walk, so locomotion, so walk and cause movement. Another function of a skeletal system is hematopoiesis, or formation of blood cells. So this is formation of blood cells. So remember, all the blood cells, the RBCs, WBCs, and platelets. Again, a review of blood. So all of this is formed in bone marrow, which is present in bones. So in certain parts of your body, you have bones which are very long. These are known as long bones. So inside a long bone, and you've all had chicken and, even if you've had turkey and other meat, when you bite through, you get the little marrow cavity inside, right? And you have this bone marrow inside. So in long bones, you will find bone marrow inside what is called marrow cavity. We'll see an image of that later. We also see bone marrow present at the ends of bones. We'll be discussing this in a little bit more detail. Ends of bone. So I'm going to erase this. So I said marrow cavity. Marrow cavity. At the ends of bones, which we'll see are given a name known as epiphysis. So ends of long bones. And then we see it bone marrow in cancellous bone. This is a type of bone which we'll see, which is also known as spongy bone. And throughout life, bone marrow is present in cancellous or spongy bones. You always get bone marrow there. In long bones, in the marrow cavity, it remains till a person becomes an adult, and after that, the bone marrow is actually replaced by fat. I don't know if you've ever noticed, if you buy, when you eat beef, for example, you get a big bone of the leg, or even in chicken, not so often in chicken, but if you get a really old cow or something and you look at the bone marrow inside, it's fatty in nature. But when it's a young cow, then the bone marrow is kind of, it's got bones, it's got blood cells in it. Spongy bone, on the other hand, whether it is old or young, spongy bone will always have bone marrow. So that's one important, it's the site of bone marrow formation throughout life. Whereas the marrow cavity is a site of bone marrow formation only in early life. In adult life, it is replaced by fat. The ends of long bones are also sites of bone marrow production throughout life, because you'll see that the ends of long bones actually have cancellous bone at that point. Then another function of bone is storage. We all know bone is made up of organic matrix, the collagen fibers and hydroxyapatite and so on, and that's what actually gives it a little flexibility. But it also has inorganic matrix. Calcium salts are deposited, phosphorus is there. So it's a site where all of this is stored. And this calcium deposition is under hormonal control. So there's a hormonal interaction, which we'll do when we go on with the system. So there are some major hormones which sort of participate in this. Also remember, vitamin D is very important for calcium absorption. Remember, we did the integumentary system, so we talked about that. The bone also produces some growth factors which have a lot to do with tissue, which help growth in the tissues. It's also a storage site where fat can be stored or adipose tissue can be stored. Marrow cavity is one example where it can be stored. So these are some functions of the skeletal system. And as I mentioned, the flexibility is due to the organic matrix, the collagen fibers and other organic substances which are present. Oh, let's go. So for some reason the text is missing. I don't know why. Well, let's see now. So you tell me, which of the following best ties the skeletal with the integumentary system? I don't know why that disappeared. So if I was to, actually, let's see, if I write here, so if I put, I don't think you all will be able to answer on this one. So if I write here vitamin B, and choice B, let's say, is calcium, and let's say here is vitamin D, and D choice, let's say, is melanin. So which of this ties the skeletal with the integumentary system? So let me see. How many people choose vitamin B? So nobody. So we make that 0. How many people choose calcium? Okay, so about three people. How many choose vitamin D? Well, the majority of the class. Okay, so I'm going to put 90% here. Okay, and melanin. How many choose melanin? No one. So that's 0. Yes, it is vitamin D. Remember, it's the vitamin D which is present under the skin, which when gets activated, that's the one which goes and helps you to absorb calcium. So that's what ties the integumentary with the skeletal system. Okay. Now here, we did integumentary system. So if you remember, I talked in the integumentary system about a condition called rickets. So what is rickets caused by? Okay, well, about half the class got it right. It's both A and B. See, you might have vitamin D, but if you don't have calcium, which cannot be deposited in bone, then it doesn't do any good, right? And you might have calcium, but if you don't have vitamin D, don't go out in the sun and you're kind of closeted in a dark space, then again, it does not help in absorption of calcium. So it's both lack of calcium and vitamin D that rickets is caused by, okay? So that's not just one. So you need both in order for bones to, to kind of get their mineral deposits. Now let's look at classification of bone. And so we classify it in two ways. One is based on structure, one is based on shape. So this one is based on the structure of bone, or what is the type of bone you see. So there are two types. One is compact bone and one is cancellous, or also called spongy bone. As the name itself suggests, compact means everything is arranged in a very dense, compact fashion. In cancellous or spongy bone, everything is not as dense or compact. It's more loosely arranged. So here, if we look at this part here, you can see this area here is compact bone. So look at this part here. This is compact bone. See, everything is so densely arranged. Can you see this? And here you can see this area is spongy bone. Can you see that it's more loosely arranged with a lot of spaces in between? And these are the spaces which contain bone marrow. And that's why spongy bone is one of the areas where you find bone marrow throughout life. So again, as a review, bone marrow production occurs in spongy bone, in cancellous bone throughout life. This spongy bone we will see is present in different areas. One of the areas it's present is the ends of long bones. These ends are known as epiphyses, which we'll come to. So therefore, the ends of long bone produce bone marrow throughout life. It's also produced in the marrow cavity of compact bone. But then in an adult, or when they are a little older, this marrow cavity is the bone marrow is replaced by fat. So bone marrow is not produced in the marrow cavity throughout life, okay, just in the early life.
Is spongy bone called something else?
Spongy is called cancellous bone.
Is there another name?
No, none that I know of. Trabecular bone, if that's what you're thinking. Yeah. The spongy bone, and we'll see when I describe it, it's also called trabecular bone because these things are called trabeculae. So that's why.
That's what it is. It's not spongy bone, isn't called trabecular.
Loosely you can call it, but that is, you usually say cancellous or spongy. And if you say trabecular, you're not wrong. But yeah, that's the other third one you're thinking of. Well, when I say adult, it's not as if when you hit 21, it's going to be replaced by fatty tissue. A little bit older, like in your 30s and so on, it kind of slowly gets replaced. It's a slow process, so it gets. A 60-year-old is more likely to have fatty bone marrow than, let's say, a 30-year-old. That way, okay? Now, here is classification of bone based on shape. So, if you look at the shape, so let's see, first one is a long bone. So if you look here, this is a long bone. It's kind of partly hidden by this one here. Let me see. So here, this is long bone. A long bone is one, as the name suggests, it's long and usually has two ends, expanded ends. And these ends we'll see are known as epiphyses, with a central area which is kind of long and is called the shaft or diaphysis. So I'm not going to write it here because I have a picture showing you that. So examples of long bones are in your appendicular skeleton. So one bone is written here, the humerus, but you have other bones in your appendicular skeleton, which you can see here. When you do these bones individually, you can see. So this is the humerus. But even this radius and ulna are long bones. The femur is a long bone. The tibia and fibula are long bones. So the bones in your appendicular skeleton, okay? Another example actually is also the clavicle. So here I'm going to write the clavicle. And the one thing you'll notice with all of the long bones that I've just shown you, the humerus, radius ulna, femur, tibia, fibula, they are all kind of vertically present in the body. Can you see that? They are vertically present. The clavicle is the only long bone which is across, which is horizontally placed. So the only long bone which is horizontally placed in the body. Okay? Only horizontal long bone. So when we have long bones, the next example is short bones. So you have here these short bones. These bones are present at your wrist or your ankle. So talus is a bone which is seen in the ankle. You also have the wrist bones which are called carpal bones. So carpals are short bones. In the ankle, just as carpals are present at the wrist, in the ankle these bones are known as tarsals. So all the tarsals are also kind of taken to be short bones. Sometimes you have bones which are kind of in between. They look like long, but they're not really very long, so they're kind of short. So you have a kind of intermediate classification which is known as long short bones. And very often the bones which are put in these are these little bones which are the bones of your hand. You know, these which are present in your palm, these are called metacarpals. The ones which are present in your fingers are known as phalanges. Similarly with your foot, they are called metatarsals and phalanges. So the examples of long short bones are phalanges and metacarpals and tarsals, carpals and metatarsals. What's that? No, they're the same. So it's these bones which you're seeing here, these and these. Okay, they are often kind of given long short bones because they kind of have some characteristics of long, but they're still a little bit short. Then we have bones which are flat. Flat bones, a very good example as given here is the sternum. Can you think of any other area in the body where bones are flat? Just by looking at the skeleton here. Yes, the skull, the top of the skull, okay, these top bones of the skull, this area of the skull here, these bones are flat, so I'm going to include skull bones in this, since you don't know the individual names right now, so some skull bones are there. Even your shoulder blade, the scapula, part of it is flat. Only part of it is flat. So it's often usually taken as part flat and then irregular also because it's got an irregular shape. So the scapula is this one here, your shoulder blade. That's the scapula. And if you look at this bone, the hip bone, when you do the hip bone in the lab, you'll see this area of the hip bone, which is called the ilium. This part is also flat. So just the ilium part of the hip bone is also a flat bone. A part of the scapula is also flat. But the sternum and the skull bones are really good examples of being flat all around. And what is important about flat bones is that these bones are made up of spongy bone on the inside, and they have a very thin layer of compact bone on the outside. So if I took a section of the sternum, for example, I would have the center made up of spongy bone like this. And then I would have a thin layer of compact bone, just a very, very thin layer on the outside. Okay, just a very thin layer. So this is true everywhere, in the skull bone, in the sternum, in the hip bone, in all of these flat bones. Then another bone that you find, which is another way of classifying bone, is where the shape of the bone is very irregular. You can't give it a definite shape. The vertebra is a very good example. You can also include in this, you can also include scapula because it is also very irregular in shape. Then your heel bone, the bone of your heel bone, which is actually called the calcaneus. When you go to the lab, take a look at that. this part here, this also is an irregular bone, very irregularly shaped. So even though it's a tarsal bone, can be included in a short bone, we often also include it in an irregular bone, okay? Then we have bones which are called sesamoid bones. These are bones which develop in tendons of muscle, so they develop in tendons and they help to prevent friction between the tendon and bone. So they develop in tendons. One very good example is your kneecap, which is called the patella. So the patella is an example of a sesamoid bone. So it helps to kind of prevent friction between, if this patella was not here, there's a muscle here which we'll do when we do muscular system called quadriceps femoris. That bone, that muscle would be constantly rubbing against the knee, the femur, and it would get worn off. So the patella develops there, so it prevents that. It also helps to increase the blood supply to the tendon. So that's a really good thing. One feature of sesamoid bones is these bones lack an outer covering which is called periosteum. Remember when we did bone, we said it had a covering called periosteum. Sesamoid bones do not have periosteum. So this is an important thing to remember. So if they don't have periosteum, they cannot heal properly. Periosteum is very important for growth and repair. So if this patella gets fractured, healing does not occur well. You usually have to wire it up. And then finally, we have bones which are known as Wormian bones, which are here. These are little bones usually seen in the skull, and these are not sort of separate bones. What happens is that when the bones are beginning to ossify, that means, they were first cartilage or they were membrane and they become bone, small bits remain as islands. So imagine this is one bone here and this is another and then there's this fourth. So imagine a little island gets separated out like this. So this looks like it's a separate piece of bone, so it's known as a Wormian bone. It's really part of this bone, but during that ossification process, it got separated and, became a separate bone by itself. So while we have 206 bones in the body, you might find people will say, oh, they are 208 or they have 210 because these Wormian bones are there. They're not true separate bones. You don't have a special name for each one of them. They're just bits of bone which, when ossification occurred, they kind of got separated and became like a little island, okay? And so they are seen in the skull. They don't, normally never see them anywhere else. So that's why I showed you here in the skull bone. It's a little small. I think you can see that, but you can see it. So now let's look at compact and cancellous bone and look at them in a little bit more detail. So when you look at compact bone, I told you like it's very dense. So it has a very organized structure to it. Cancellous bone, on the other hand, it's like networked. So it's kind of not as organized. So in compact bone, the functional unit of the compact bone is what is known as an osteon. So osteon is the functional unit of a compact bone. And each osteon, and if you pay attention here, each osteon consists of a central canal which has blood vessels, as you can see, blood vessels and nerves and lymphatics. And surrounding this central canal are rings of bone plates which are known as lamellae. So this is the central canal, or also known as the Haversian canal. So the central canal is also called the Haversian canal. And this is surrounded by bone plates which are present as rings around it, like the rings of a tree. So this is one osteon. So the number of bone plates that it has is not kind of set. It's not necessary it has to have only 2 or 4 or 6. It can have, usually like about 4 to 6. So these lamellae, because they are going around the central canal, they're going sort of in a concentric manner or a circular manner. These lamellae are known as concentric lamellae. Concentric means going around in a circle. So can you see this? These lamellae which go around the central canal in an osteon is known as a concentric lamellae. See this? Concentric lamellae. So you have many osteons. Can you see that? Many osteons. The space between osteons is, sometimes it's not possible to have a perfect osteon. So you have some space present in between. So imagine if I have osteons like this. Can you see these spaces which are present in between? You can't have another osteon. Instead, you just have bone plates filling in between. So those lamellae are known as interstitial lamellae. Can you see this? Interstitial lamellae. So interstitial lamellae are bone plates between osteons. And then you have lamellae which encircle the compact bone all the way around on the outside and all the way around on the inside. So they don't encircle just an osteon, but they encircle the whole part of the compact bone. These are known as circumferential. Circumferential means going around the circumference. Okay? So imagine, for example, let's say if this was a piece of bone. Suppose I took this piece of compact bone, showed you like this. Circumferential lamellae will be on the outside and they'll be on the inside. You'll have the osteons up here. And you'll have the interstitial in between them. Do you see that? And that's exactly what this picture is showing. So see the circumferential lamellae, these are outer and these are inner circumferential lamellae. Do you see that? Okay. Now on the outside of bone, this outer covering of bone is covered by a layer, a membranous layer, which I can say is like the skin of the bone. So this membranous layer is known as the periosteum. It's very important, peri meaning on the outside, osteum meaning bone. So it's on the outside of bone. And you can see here it has two layers, and what I want you to pay attention to this is inner osteogenic layer. This periosteum actually has cells inside it. These cells are like stem cells. So they are capable, if bone ever gets fractured, the fracture heals from cells which come from the periosteum. Okay, so it has cells which are capable of growth and repair, which can provide growth and repair, the periosteum.
Why is it that when you get older and say people, or have fractures, and have to go through all that, how come it takes longer for them to heal than somebody younger?
Okay, why do older people take longer to heal? With age, everything slows down, right? So that's basically it. The periosteal tissue, blood supply has decreased. The periosteum is not as, cannot be stimulated as much as it can, in a younger person. So young people always heal better than old. So it's just a process of old age. That's all. Nothing more to it, yeah, that's it. Then let's look at, so we see that, and let's look now at spongy bone. So that was compact. You see, you can see the lamellae, the osteons, which were the functional units. Lamellae, the central canal was the Haversian canal, and yes, we have one more canal called the Volkmann's canal. So if you look at these central canals, they run vertically like this. Can you see that? Now these are actually fed by canals which begin from the outside and connect these Haversian canals to one another, and these canals then finally lead into the spongy bone, because spongy bone is on the inside, compact bone is on the outside. It has to be, you want something stronger on the outside and something weaker on the inside. So these horizontally or transversely running canals, these ones, they are perforating. Can you see they go through and perforate and go through? These are the ones which are called Volkmann's canals. So another name for them is perforating canals. And what they do is they carry blood vessels. So perforating canals are also called Volkmann's canals. So they carry blood vessels to the central canal. And so they've given this central canal a branch, then they continue, give this one a branch, then go in and go into this spongy bone and spread out in between the trabeculae where they'll form the bone marrow in the spaces.
Is that in compact or is that in...
This is in compact. All of this is compact bone. See, from here to here is all compact bone. Yeah, that's okay. So pay attention to the figures real well, because the whole story is actually told there. Now let's look at spongy bone, which is this area here. See, there are no osteons, right? everything is very loose. So here the bone plates, instead of being in this organized fashion, they are kind of networked. So they, instead of calling them lamellae, we call them trabeculae. The word trabeculae means like a network. So these are trabeculae, which is why it's called trabecular bone too. So that's the difference between spongy and compact. But otherwise, the common features between them, and when we did bone tissue, remember all bones, if you remember, they had those osteocytes which were caught in between. You remember when we did bone tissue? So here, these are your osteocytes which you see lying in those lacunae. And inside trabeculae also, when you look at trabecular bone, here also you'll have an osteocyte. And then connecting the osteocytes, you have these little thread-like canals which are known as canaliculi. So this is again a review just of bone tissue, and even in trabecular bone you'll have these canaliculi, because all canaliculi do is connect one osteocyte to another and then to the central canal, and they help to transfer nutrients and waste products, right? So you'll see canaliculi in both in both compact and spongy bone, and you'll see osteocytes in both compact and spongy bone, okay? The differences is you'll see these lamellae, the different types of lamellae in compact, but you'll see trabeculae in spongy bone. Yes? Yeah. You had a question? Canaliculi is to connect each osteocyte with the one next to it so that it can transfer nutrients and also remove wastes. And so transfer nutrients from the central canal and bring back wastes to the central canal where it will be removed by the veins. Okay? Now, suppose you wanted to do a bone marrow biopsy. Which of the following bones would you select? So here's where you've got to think a little bit critically. Okay, the correct answer is the sternum. The correct answer is the sternum. And here's why. Think of this. Your femur is way deep inside your thigh, right? So many muscles. Imagine what a long needle you would have to poke right through your thigh to get that bone marrow. Now, if you were an adult, right, let's say you were 40 years old, there's no point. That would be marrow cavity filled with fat, right? Same for the radius. Radius also deep inside muscle. The vertebra, very difficult, again, it's at the back, very difficult to get to the body of the vertebra. The sternum, if you remember, I told you the sternum was made of cancellous bone. You remember cancellous bone is a site of bone marrow production throughout life. Also think about it, here's your sternum. We can all feel our sternum quite easily. It is subcutaneous, so easy to remove bone marrow from there. And more importantly, it will contain bone marrow. You're sure to get bone marrow from there because it contains a cancellous bone, and cancellous bone produces bone marrow throughout life, okay? So two areas where we commonly do bone marrow biopsies, though that's becoming a little rare now, is the sternum, and we also do it from the ilium. Remember the hip bone, I said that part of the hip bone was flat, so from the iliac crest, which is easy to feel. So in children, we often do it from the iliac crest, because again, a site of bone marrow production, always very easily accessible, and you can remove that. Now here let's look at the parts of a long bone. So we called it a long bone when it had two ends, two expanded ends, and a central region connecting the ends. The ends of the long bone, the two expanded ends, are known as the epiphysis. The central part is called the diaphysis, or it's also known as the shaft. The epiphysis is the area where the bone articulates with another bone. So usually joints are formed in that area. See, the epiphysis is where a bone will articulate with, because it's the end of a bone. So that's where it will join with another bone to form a joint. So if you remember when we did cartilage, we said there was something called articular cartilage, which is present over the ends of long bones. So here, that's why you see articular cartilage here and you see articular cartilage here, which tells you that this is the part where a joint is going to form. Okay? So this is showing you the humerus. So this is where the shoulder joint will be and this is where the elbow joint will be. So you can see the epiphysis is covered by articular cartilage. During growing periods, when the person is still young and the bones have not fused, many of our long bones actually develop in cartilage and then they are replaced by bone. So you have bits of cartilage between the epiphysis and the diaphysis. So between epiphysis and diaphysis here, between epiphysis and diaphysis here. So that cartilage which is present in between is known as the epiphyseal cartilage. So it's not shown here, but this is where you would have the epiphyseal cartilage between the epiphysis and the diaphysis. This allows the bone to grow in length. So when we do ossification, you will see it allows the bone to grow in length. When the person stops growing, this cartilage is actually then replaced. It's taken over by bone totally, and its replacement is what is called an epiphyseal line. So epiphyseal line is where the epiphyseal cartilage used to be. Okay? So the epiphyseal cartilage is a growth cartilage which is hyaline in nature. It allows the bone to grow in length. It is present between the epiphysis and the diaphysis. So this is the area where you will see this. Don't worry, we'll see more pictures of this. This is the area where you'll see it. When the bone completely ossifies, that means it becomes all bone, that cartilage is gone and it's replaced by bone, and that area is represented by a line which is called the epiphyseal line. Bones are very, very vascular. Most bones are, you will see a very large artery entering the bone, and then that artery is the one which gives off those various branches which go into the workman's canals, and then its branches into the central canal. So that main artery which goes to the bone is called the nutrient artery. And usually when you look at the direction of the nutrient artery, you will see that the growing end of the bone is the opposite end. What do I mean by growing end of the bone? Remember I said that you had an epiphyseal cartilage here and you had another one here. Now they don't both fuse at the same time. That means they don't both become bone at the same time. One usually fuses first, this remains cartilage for longer, and this fuses later. The one that will fuse later is often called the growing end of the bone. Okay? So this nutrient artery, whichever direction it goes, the growing end of the bone, it's easy to tell. If you look at a true bone, if you look at a real bone, you can actually see the nutrient, the hole, the foramen for the nutrient artery. The growing end of the bone is the opposite end. So if the nutrient artery's direction is this way, the growing end will be the lower end. Okay? That's just an interesting piece of information to give you. So it's generally seen that for the upper limb, the growing end is towards the shoulder and towards the wrist. So at the shoulder, the head of the humerus is the growing end, and at the wrist, the lower end are the growing ends. It's just one of those. And in the lower limb, growing ends are towards the knee. Okay? Then here is we all talked about the hemopoietic function, the formation of bone marrow. So here you can see how the bone marrow is actually replaced by fat, where it's called yellow bone marrow. But in young people and early adulthood, this would be bone marrow. So it's a site of bone marrow production. But the epiphysis, if you look at the epiphysis, see here, the diaphysis is all compact bone. See this? It's all compact. But the epiphysis is spongy bone. So that's why the ends of long bones are sites of bone marrow production throughout life. Then I also want you to look at the periosteum. So here you can see the periosteum. This part, this covering here is the periosteum. So here is the line, it shows you here. So here is the periosteum, and here it's kind of been removed. So here you can see the periosteum which has been peeled back. And this marrow cavity here is lined by endosteum. So see this up here, medullary cavity. The marrow cavity is also called the medullary cavity, lined by endosteum. So here is endosteum lines the marrow cavity. It also lines those trabeculae. So if we go back, so it also lines these trabeculae. The endosteum also lines this, and the periosteum lines the outer surface of bone. Both are important because they are sites of osteogenic cells, cells which can help to repair and grow bone. Okay. Now here you can see these fibers which are present. I said this periosteum has been peeled back, and notice these little fibers. These are collagen fibers. These are called Sharpey's fibers. They're actually part of a tendon. So when a muscle is here and the tendon of that muscle passes through the periosteum and goes to the bone, and these fibers which pass through and go to bone are known as Sharpey's fibers. So they're collagen fibers which pass through the periosteum and go to the bone. So what do you think is the function of the Sharpey's fibers? Why do we have those Sharpey's fibers? Okay, the correct answer, it helps to pin the periosteum to the underlying bone. And if you think of it, what is one of the functions of the skeletal system? Remember, provides attachment for muscles, right? So here, that's why I was drawing it. So here you have a muscle belly, and here is the tendon, and the tendon has to attach. If you want it to attach real strongly, and the periosteum was like a skin. Remember when we did integumentary system, we had epidermis and dermis, and how we had those papillae where they interlocked, and that's how they kept the two together. Similarly here, so if these of collagen fibers pass through the periosteum and go to the bone, they help to pin it down. I know you all saw this blood vessel. I'm glad you're looking at images. You saw this blood vessel and you saw this blood vessel passing through the periosteum, so you thought that's why, so I can quite understand. But that's not its function. The function is to pin the periosteum to the surface of the bone. If it was not pinned, it would come off very easily. Okay? Now here let's look at cells of osseous tissue. So whenever you think of cells, you must always know their functions. So first are the osteogenic or stem cells, and these are the ones which are seen in the periosteum and the endosteum. These are mitotically active, so that's why they help. That's why the periosteum and endosteum helps in growth and repair of bone. The next cell, and we've done these cells, the next cell is the osteoblast, which is the cell which lays down bone. And here it just describes it differently. It's the matrix synthesizing cell responsible for bone growth. Remember, the matrix synthesizing meaning laying down bone. So this is the cell which lays down bone in layman's terms. When they lay down bone, like they lay down the lamellae or the trabeculae, then they get caught in between, and that's where they become osteocytes, which are mature bone cells. Their function is actually, first they didn't know what their function was. Now they think that the function is to monitor the stresses and all the influences that happen, like when you walk a lot, for example, you're stressing the bone. So they sense that stress is coming from this area, and then they will kind of signal to the osteoblast and osteoclast to do their job. So they tell the osteoblast, you need to lay down more bone over here. And they'll tell the osteoclast, bone is not needed here, remodel, remove bone from this area. Okay? So that's how they kind of connect to the osteoblast and osteoclast, by monitoring what's going on around them. Osteoclasts are bone resorbing cells, or what we said that osteoclasts are bone removing cells. And just this evening I gave them an example, the way you can think of it. Clast is clawing, it's removing bone, so that's how you can remember that. So is this true or false? I kind of gave away the answer a little while ago. This is true. The periosteum and endosteum both, because they have these osteogenic cells, both are responsible for growth and repair. Okay, sorry. Yeah, go ahead. Now let's look at ossification. All this while I kept talking about when the bone ossifies, the growth plate is removed. So what is ossification? It's the purpose where bone is actually formed. And there are two types of ossification that occur in the body. One is called membranous ossification, where bone develops from a fibrous membrane. Again, when we did tissues, if you remember, I mentioned something known as mesenchyme, which was primitive. These are primitive cells which which change into fibroblasts and other things, and they can lay down connective tissue. So there is this fibrous primitive connective tissue called mesenchyme, and this changes into bone. This occurs very fast. It's a very quick type of ossification, because you just have a one-step process. From mesenchyme, you get bone. Then the second type of ossification is known as endochondral, or sometimes also called enchondral ossification, where first cartilage is formed. So actually mesenchyme forms a cartilaginous model, and then the cartilage is replaced by bone. So it's like a two-step process. So this obviously takes a little longer. Now, where ossification first begins, that area is called the primary center of ossification. Primary centers of ossification always, for all practical purposes, we'll say always occur before birth. So they occur inside the uterus in what's called intrauterine life, and they're always seen in the diaphysis. Secondary centers of ossification, again with a few exceptions here and there, they always occur after birth, and they are seen in the epiphysis. So important facts to remember. Primary before birth in the diaphysis, secondary after birth in the epiphysis. Then there's two types of growth. Interstitial growth, which is growth in length. So it occurs in a vertical fashion in many bones. And appositional growth is growth in width. So I would say transversely. So it's growth in width. Appositional is the bone thickens and grows in width. Interstitial, the bone grows in length. So let's look at these ossification processes. So I want you all to read these. So I'm not going to kind of read each one of these bits for you. So I'll give it to you in quick, short form, and then you can read this. One thing about membranous ossification is it usually occurs in flat bones, not all flat bones, but many of the flat bones. So the skull bones ossify in membrane, especially the top part of the skull. They ossify in membrane. Another bone which ossifies in membrane is the clavicle. So that long bone which was horizontally across, it actually ossifies in membrane. So how does this ossification occur? So first, if you look at it, you will see that this is all membranous tissue. So it's this connective tissue or primitive mesenchyme. And so that's why you have these mesenchymal cells. And in the center, when ossification has to begin, in the center, the cells kind of start growing, getting larger, and they kind of change into special cells which are called osteoblasts. So these cells here, that's where ossification starts. So this is known as the ossification center. Here they don't have anything like a primary and a secondary ossification center. Okay, that primary and secondary is seen in endochondral ossification. So here these cells, so they begin to get large, they begin to secrete, they kind of get blood vessels, they attract blood vessels towards them. There's deposition of calcium. That calcium gets deposited on these fibers, and that's known as matrix. Remember, matrix is formed of ground substance and fibers. So that gets deposited. Some of the cells get trapped in between. These cells are known as osteocytes. Remember those which get trapped. So this way, the cells then on the outside, they keep forming, depositing these osteoid matrix, and cells get trapped inside. They keep sort of pulling blood vessels towards them. So the blood vessels go into the spaces, and that's how those trabeculae get formed. So you can see this, it began like this, it attracted blood vessels, they'll go in between the spaces. So this kind of laying down of osteoid matrix occurs in a haphazard fashion, which is why spongy bone kind of is, it's not very organized. It's kind of, the network can be in any fashion. So this is where all of the spongy bone is present. On the outside, a thin layer of compact bone develops. So just on the outside, a thin layer of compact bone develops. If I was to describe, remember I told you the sternum or all flat bones, they are spongy on the inside, but they have a thin layer of compact on the outside. So you can see this is where the thin layer of compact bone will be present on the outside. It will replace that spongy bone, okay? So that it gives it strength. Otherwise, it would break very easily. So this is how membranous ossification occurs. Let's see how endochondral ossification would occur. So here first the membrane, and that part is not shown. The membrane actually, so you have a membrane which forms a cartilaginous model. So it changes and actually forms a cartilaginous model of the bone which will finally form. So here is the cartilaginous model which is forming. So on the middle of the cartilaginous model, the area where the diaphysis is, at this point over here, the cells kind of change, these cells, and they become osteoblasts, and they lay down a bony collar over here. So this is known as the bony collar. At the same time, while this bony collar is being laid down, in the center of the diaphysis, again the cells in the middle, the cartilage cells, they begin to expand and grow large. When they grow large, they again attract few blood vessels, and those blood vessels deposit calcium. So when calcium is deposited, those cells no longer can get their nutrition, they begin to die. Meanwhile, this bony collar which is present, it takes blood vessels, more blood vessels inside, and with the blood vessels it sends in osteoblasts. Those osteoblasts replace those dying cartilage cells. So can you see here now, this area is all dead, and now those dying cartilage cells are replaced by those bony cells which are present. So bone is replacing cartilage. At the ends up here, this is the area where the growth plate is present. So as this bone is replacing cartilage, this growth plate keeps dividing. So there's an area here, you can see this part is cartilaginous. It keeps forming more cells, and it keeps adding more cells, so it grows in length. Can you see from this it became like this? So as these cells which are larger come lower down, they keep getting replaced by bone, and the cells higher up are much smaller. So it keeps growing in length in this fashion, in a vertical direction. So here you can see this is a pretty grown, full-grown sort of model. Here you can see a lot of the cartilage has been replaced by bone. Osteoclasts also come in, and they kind of eat away some of those bony trabeculae which are present here. So that's how they end up forming the marrow cavity. At either end, this is the end which will form the epiphysis. Here's where the secondary center will begin to appear. So can you see now the same thing happens here, but instead of forming lamellae like you find in compact bone, here it forms trabeculae because this area is going to be spongy bone. So here this epiphyseal plate will continue to be present as long as the child grows. Usually by about 18 years in females, 18 in females, and by about 21 years in males, all bones have completely ossified. So we say that those growth plates have fused. How do those growth plates fuse? So I remember I said these growth plates, what they are doing is they are kind of making cells. They keep adding cells here, they keep adding cells, these cells keep getting replaced by bone. As they keep adding, the bone keeps increasing in length. At one point, that increase in length stops because this bone deposition is faster than cartilage formation. So as this bone deposition kind of overtakes cartilage formation, this epiphyseal cartilage gets completely replaced by bone. So now there no longer can growth occur in this linear fashion. So it occurs at one end first, and then it occurs at the other end, over here. So now it is completely bone, okay? At the ends, however, the articular cartilage remains, because remember, that has to remain. So that cartilage does not ossify at the ends. It remains as articular cartilage. You had a question, you had a hand.
Those plates, the
Epiphysis?
yeah.
Yeah.
When you're looking at growth plates, is that what they're looking at when they do like scans to see how much someone's going to grow?
By looking at a growth plate, they can't tell how much someone's going to grow. They can tell you whether growth is still possible, because if they see the epiphyseal plate, they say, okay, the plate is present, this child can still continue to grow. Sometimes growth plates fuse early. So then if they see that the growth plates have fused, then they say the child will not grow anymore, right? Because they're fused, so no longer bone can't be formed.
So do they look at how much is left to see?
If they find an epiphyseal or growth plate present, they can tell that, okay, the child still has the potential to grow. Yeah, they can't tell you how many years more the child will grow. That is very difficult to tell, okay? So here let's look at endochondral ossification. It actually tells you both.
If you have a dog with bad breath, you need to watch this video to the end.
We invented a product called bone formation, also known as osteogenesis or ossification, is the process by which bone tissue replaces embryonic connective tissue to form the skeleton. From childhood to early adulthood, ossification lengthens and thickens bone. In addition, the process of ossification is used throughout life to remodel bones. There are two methods of prenatal bone formation. During intramembranous ossification, bone is generated on or within fibrous connective tissue membranes. As the process begins, mesenchymal cells differentiate into osteoblasts in regions called ossification centers. The osteoblasts secrete osteoid or uncalcified bone matrix. Over a few days, osteoblasts become osteocytes, and calcium and other mineral salts are laid down, hardening the matrix. The bone matrix develops thin columns of bone called trabeculae, which fuse to form spongy bone. Blood and lymphatic vessels grow into the surfaces of the newly formed bone and develop red bone marrow. Outside of the bone, a dense layer of connective tissue called the periosteum forms. Most outer layers of spongy bone are eventually replaced by compact bone, but the center remains spongy. Intramembranous ossification also occurs with skull bones in childhood. At birth, skull bones are separated by fontanelles, or soft spots, and sutures, immovable joints made of fibrous tissue. Fontanelles in the fetal skull allow for easier passage through the birth canal and rapid brain development. Up until adolescence, the fontanelles slowly ossify into sutures, providing the brain with greater protection. Endochondral ossification, the replacement of cartilage by bone, occurs in most bones of the skeleton. The process begins when embryonic mesenchyme condenses, forming the cartilage model, the shape of the future bone. The model grows within the fetus. Lengthwise growth is attained via interstitial growth. Width is attained via appositional growth. A nutrient artery penetrates the perichondrium, increasing nutrient availability to the cells. Osteogenic cells are stimulated to differentiate into osteoblasts. These cells secrete matrix beneath the perichondrium that forms a thin shell of compact bone known as the bone collar. As the perichondrium begins to form bone, it is now called the periosteum. The bone collar reduces diffusion to the cartilage inside the model, depriving it of nutrients. Capillaries grow into the disintegrating cartilage, delivering osteoblasts. The new growth forms a primary ossification center, an area where bone tissue will replace most of the cartilage. Osteoblasts deposit bone matrix, building spongy bone trabeculae. The growing model is gradually remodeled. The cavity fills with capillaries and red bone marrow. Ossification proceeds, forming the main portion of a bone, known as the diaphysis. Around the time of birth, blood vessels enter the epiphyses, the ends of a bone, forming secondary ossification centers. Secondary ossification differs in that no medullary cavity forms, and ossification proceeds outward. As a result, the interior of the epiphysis remains spongy. Secondary ossification leaves a thin layer of hyaline cartilage covering the epiphyses. This is known as articular cartilage, and it reduces the friction and shock in bone joints. The change to the epiphysis also forms the epiphyseal plate, a layer of hyaline cartilage that enables the diaphysis to grow in length.
So when growth stops, the epiphyseal cartilage is completely replaced, and that's where you get the epiphyseal line. So let's stop here, and we'll continue with this